Alright, so we're going to attempt a fairly challenging physics problem here, kinetic energy type problem. The figure shows a cord attached to a cart that can slide along a frictionless horizontal rail aligned along an x-axis. The left end of the cord is pulled over a pulley of negligible mass and friction, and at cord height h equals 1.2 meters. So the cart slides from x1 equals 3 meters to x2 equals 1 meter. During the move, the tension in the cord is a constant 25 newtons. What is the change in kinetic energy of the cart during the move? So first inclination when we're solving for kinetic energy, right, we want to know as the cart slides from x1 to x2 what's going to be its change in kinetic energy. So pretty quickly we'll want to think delta KE equals initial kinetic energy minus final. So we don't actually know if it starts from rest or not, but we expect this to change to depend on the change in velocity, right? 1/2 m, and I'll just say delta v, right? V final minus v initial squared. But the issue is that we don't really know anything about the velocity, and we don't know the mass. So pretty quickly we realize that this is not going to work for us. So we got to think about it a different way. And potential energy is probably not going to come into it because the car is not changing vertically, it's only moving horizontally, so there's no gravitational potential energy being increased or decreased, and there's certainly no springs here. So the way we're going to probably have to go at this, if we're not going to do this, is using work. So the change in kinetic energy acquired, the kinetic energy acquired by the cart is occurring due to the work that's being done on the cart. And what is work? Well, work is a force over a distance. And indeed, we have a force being applied. We have this tension force which is pulling the cart, and it's moving a distance. So this looks promising. But the problem here is that the actual displacement of the cart is in the purely horizontal direction. It's moving purely horizontally from x1 to x2 with no vertical change, whereas the force being applied to it, the tension, is being applied at an angle. So we have to include the angle when we do that. But there's a problem with that as well. So I'm going to blow this picture up a little bit, and hopefully you can see why this is problematic. So let's see if we can try to draw this. So this is x1. That's where the cart is initially, so I'll put it right there. And then at some final point, it's at x2, which is here. And when it's in its final position, the pulley, since the pulley's up here, its cord is pulling it like that, right? At the beginning, the tension force that's acting on the cart is in the direction of the pulley, which is directly toward the top of the pulley from its initial position. But then in the future, at its final position, the tension is occurring in the direction of the cord at that point in time, which is directly to the top of the pulley from a different position. So the direction is different, and at some intermediate point, if you can imagine that maybe it's halfway between x1 and x2, then the cord would be at yet another angle. So this angle theta, which we can find, is different from this angle theta, is different from this angle theta. So we can't really use this formulation because theta is different at every moment in time. As the cart slides from one side to the other, theta is constantly changing. So we cannot simply take the tension force and resolve it into its horizontal component and let that horizontal component of the force be aligned with the displacement. What we have to do instead, so we're going to throw this away, what we have to do instead is simply find the displacement. I shouldn't say simply, I mean it's going to take some geometry, right? We have to find the displacement that's aligned with the tension. In other words, how much of the cord would have to be pulled past the pulley in order for the block to move from x1 to x2. And that's what we're going to solve for. So as the cord goes from x1 to x2, as the block goes from x1 to x2, how much of the cord goes past the pulley? How much has to be pulled through here to make that happen? That's what we're going to find. So let's look at our drawing. If we know that when it's in its initial position, we have, let's dimension this a little bit. The height is 1.2. So that's from the top of the pulley to the reference point. Well, actually, the reference point should really be the top of the mast, but I'm going to do that there. And then the distance between x1 and x2 is from 3 to 1. So this is 2 units long. That's just from here to here. And then we're assuming this is the origin, which wasn't readily apparent from this drawing, right, that the origin's actually right here. But that is the case. So that's to get from 0 to 1. That's 1 unit here. So that's 1 unit in length. This is 2 units in length, and it's 1.2 high. So that gives us most of what I think we need to know. We can find the length of the hypotenuse, right? Right, so we can find that whole hypotenuse of the big triangle. And then we can just take this triangle here, and since we know its base and height, we can find its hypotenuse. And if we subtract the two, so we need some variables here. Why don't we call this x and call this y? If we can subtract from the initial position, this big hypotenuse x is that full length, and we subtract from that y, which is the length of the smaller triangle's hypotenuse when it's in its final position, we can find how much of the chord has went past the pulley as the mass went from x1 to x2. So that's what we'll do. So the distance that we want for our formula here, so now I'm just going to write FD because the assumption now is that the F and D are aligned. We're using the tension that's acting in a constant tension that's being pulled past the pulley, and the distance, which is always aligned with the tension. Even though the tension's direction is changing, the distance is changing as well, but they're always aligned, so we don't need the cosine theta anymore. So that distance is x as we've defined it above, minus y as we've defined it above. And x is, we can get from Pythagorean theorem, we have a triangle with base 3 and height 1.2. So that's 3 squared plus 1.2 squared square root minus y, which is the hypotenuse of the smaller triangle, which we can also get by Pythagorean. That's 1 squared plus 1.2 squared square root. And when we solve that, we get 3, I'm doing this on a calculator. That first part is 3.23. By the way, this is meters. I'm not showing the units here. 1 squared is 1, obviously, plus 1.2 squared square root is 1.56. So the difference between those two is D. That's how much was pulled past the pulley. 3.23 minus 1.56 is 1.67 meters. Always aligned with the tension force at every point, at all the intermediate points between x1 and x2. So at last we can say force times distance equals a constant 25 newtons times 1.67 meters, which is 41.75 joules. That's joules of work done to move the block from x1 to x2, which implies that since there's no change in potential energy, all of that work must have been converted into kinetic energy now that the block is in motion. All of this is done without ever knowing the mass, without ever knowing the velocity, without ever considering the acceleration. So this is the formulation just using work to find kinetic energy. And that's it.